didn't take too many steps to resolve to contradiction, right? So that was good. Okay. All righty. That is good to know. All right. So we are now on to discrete probability. And the topic that we were on, oh no, not this one. That was a mobile programming apps stuff. Okay, so we are doing coin toss, okay? Well, birthday we talked about already. So the last topic where we left off was talking about, when we toss a coin, okay, what are the chances that out of 5, coin tosses, we end up with like a total of 2 heads and 3 tails or something along that line, okay? So that was a question. So now we look into this and say, okay, how do we cast this into the terms that we understand? So the first thing is, what is omega? So omega is basically asking, what is the set of all the possible outcomes of this experiment? Well, this one is pretty easy to understand, right? Because each trial has 2 possible outcomes, head or tail, and we have 5 trials, in this particular setting per experiment. So the total number of outcomes is just going to be 2 to the power of 5, okay, which is what, 32, right? Okay. So the second question is, but what events are we interested in? So we're interested in, let's just say that, we're interested in, out of the 5, coin tosses, we're interested in the outcomes that consist of 3 heads, okay? So we want to know what are the chances that out of 5 coin tosses that we'll end up with 3 heads as a result. The other ones are obviously tails, because if they are not heads, they have to be tails. So are we okay so far with how the problem is set up? Okay. So we know what is the cardinality of omega already, because it is 2 to the power of 5. Okay, so that part is established. We know what the denominator is when we try to figure out the probability. But what we do not know yet is what is the cardinality of E, because E is the set of all the events that we are of all the outcomes that we are interested in. So that's going to be, head, 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 tail, tail, head, tail, head, and so on and so forth. So the question is, how many of those do we have? What do you think? How do we systematically figure this out? What do you think? You can, okay, so, but it's not exactly permutation, because in this case, it is with replacement. After you get a heads up, after the first coin toss, the second one can still be heads up, right? So that means you cannot eliminate, you cannot remove a choice for the second trial, for subsequent trials. So the first thing we do is we code this slightly differently. So we look at this one, which is the configuration of a particular outcome from a coin toss experiment, which is head, head, tail, tail, head, okay? So instead of using a 5 tuple to represent the result of that particular experiment, of that particular outcome, we now use a set to represent the same thing. So can someone tell me how these two relate? Head, head, tail, tail, head versus 0, 1, 4.
I guess you're looking at the outcome, head, head, tail, tail, and then head as like an array. And then
Exactly.
The first head was the 0th element.
Yep.
Second head is the first element. And
Exactly.
the third head is the 4th element.
Good job. That's exactly what we are doing, okay? So we are now representing the outcome of this experiment not as a 5 tuple anymore. Instead, it is now represented as a set of indexes, okay? What indexes are we talking about? Those are the indexes of individual trials that has the outcome that we want, which is a head. So now we say, oh, this thing here, this outcome, which is head, head, tail, tail, head, has what we want in the 0th trial, the first trial, and the 4th trial. What about the other 2? Well, not something that we want. That's why they're not in the set. Is that okay? Yep.
Could you have done the same thing just with tails? Because I think...
Yeah, you can do the same thing with tails. So if you do the same thing with tails, then we'll be encoding this as 2, 3. Because trial 2 and trial 3 are tails. Yep. So you could do the same thing. It's the flip side of, this one here. Okay, so the problem is now changed from we're doing experiments, with replacement and a certain number of trials to something else. Yes, go ahead.
You just have like a set of indices and choose 3 from them. So like
Exactly. So now we are. So how many indexes do we have in total? We have 5 because we got 0, 1, 2, 3, 4, right? So we got 5. Out of those 5, how many do I want to choose? 3, because that's what the problem is saying. I'm interested in all the possible ways that ends up with 3 heads in 5 tosses. So it becomes 5 choose 3. Is order important? No, because we're talking about a set. So order is not important, 5 choose 3, so we are using combination. So it's the number of combinations of choosing 3 out of 5. And we already know how to do that. So if I scroll down a little bit, you will see the equation to do that. So it is basically 5 choose 3, which can be written this way, or you can have a C and then 5, 3 as parameters. But this is the kind of, I guess, mathematician way of writing 5 choose 3. Oh, okay. So if the cardinality of E, which is the set of all the outcomes that we are interested in from the experiment, is 5 choose 3, and the total number of possible outcomes is 2 to the power 5, now we can actually figure out the probability, which is 5 choose 3 over 2 to the power of 5. Is that okay? So if you want to, we can actually do the computation and figure it out. So let me just pick one spreadsheet and make a new one, because I'm just using this as a calculator. And we can just figure it out. Okay, so we are looking at combin 5, 3 and divided by power 2, 5. And the answer is about 31% of the chance. So 31% of the time, okay, if you count the number of heads of 5 tosses, 30-something% of the time, that's what you get. Wait, but that's assuming the coin is not loaded, right? Because if the coin is loaded, we are not going to get this number. So does everybody understand what it means when we say the coin is loaded in a coin flipping gamble? Okay, what does that mean? Yep, the chances are not 50-50 anymore. Okay, one side has a higher tendency to show up. So in those situations, how do we figure out the probability? So that becomes the next question, right? Okay. So let's say that is the problem that we're dealing with now, okay, which is, in the notes, it's just, the next item. I'm certainly hoping that most of you remember to read the module, before the class, because, that's going to help tremendously in terms of, understanding the material. Okay, so what we now have, okay, we are focusing on this part here, okay? So assuming the coin is loaded, in other words, the chances of landing on the head and the chances of landing on the tail are not the same, okay? So we're going to say that P is the probability of landing on the head, and then Q is the probability of landing on the tail. But those two added up should be a 1, okay, assuming you cannot land on the edge and actually have it stand on the edge, okay? So are we okay with this equation here? P is the probability of landing on the head, and Q is the probability of landing on the tail, and the relationship between P and Q is P plus Q equals 1, because it has to account for all cases. Is that good? Okay? All right. So if that is the case, then we can look into this kind of strange equation here, okay? So we are looking at P plus Q to the power of 5, and it can be expressed as blah, 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 like that. Okay. So if you just forget about this side, okay, and instead of looking at this as P plus Q, and instead use 1 plus x or x plus 1, what does that give you? 1 plus x to the power of 5. What is that? kind of like a binomial thing, right? You can just expand it out and figure out, oh, we got 1, 1, and how many x's do we have? We got this many. How many x squared do we have? We have this many. How many x cubed, x to the power 4, fourth, and then x to the power 5, right? Okay. So if I use p and q, it's kind of the same deal. I mean, each term would involve a certain power of p and a certain power of q. The relationship between the power of p and the power of q is the powers have to add up to 5. Does it make sense? Because all you're looking at is how do we combine the p's and the q's when we are multiplying p plus q times p plus q times p plus q and so on. Okay, so the ki is really just the quantity of that particular product between a power of p and a power of q. And we'll figure out what ki is later on. Okay, we'll just say that we are using ki to represent the quantity of each one of those. So when you add up all of these, it should be the same as p plus q to the power of 5. Does that make sense? Is that okay? Does everybody understand what the k terms are for? They're really just a little placeholder for a particular quantity. Are we good so far? Okay. Well, I have a question. This whole equation is stupid. It's stupid because p plus q is 1. 1 to the power of 5 is always 1. Why do we bother to expand it and try to look at it this way? Why? Because we don't want to lose money. Okay? Because if you know ahead of time that a coin is loaded in a particular way, and you are gambling, and you're saying, okay, I'm going to bet on, okay, out of 5 flips, 2 would be heads, okay? You want to know whether that probability is leaning your side or not. And this can help us find that answer. So would that be enough motivation to understand why we are looking at 1 to the power of 5? I hope so. Okay. So now we look at this and go like, so how do we figure out k0 to k5, which are all basically positive integers? So what we do next is something that seems to have nothing to do with this question. So what we do is we look at Pascal's identity. We start with this part here. This is what we start off with. Okay, you look at this and go like, okay, so we're looking at the sum of n choose k and n choose k minus 1. Okay, fine. What is the big deal? Well, scroll down a little bit. And through all the derivation, we conclude that that turns out to be the same as n plus 1 choose k. Okay, this is called Pascal's identity. So let's just go through the derivation a little bit. I know how you guys really love these derivations, but since I spent the time to do it, now you have to spend the time to learn it. All right. So the first line. What did I do on the first line? Yep, I'm just using the definition of combination. So n choose k expands to n factorial divided by k factorial times n minus 1 the whole thing factorial. And then the other one is kind of the same way, okay? Except we don't have k, we have k minus 1. So we just expand out by definition. And what about from line 1 to line 2? What is the derivation from line 1 to line 2? All I did was to use associative rule and rearrange this part here just a little bit so that it looks like this. Huh? Yeah. Yeah, it's basically distributive, not distributive. It's associative rule. Because when you look at n minus k minus 1, the whole thing, k minus 1 in parentheses, it is the same thing as n minus k plus 1, right? Then you can shuffle things around and move the minus k here and then the plus 1 outside of the parentheses. So are we convinced that from 1 to 2 is like a simple algebraic manipulation. Okay. From 2 to 3, what did I do from 2 to 3? Multiply the top and the bottom by k. So I multiply the k to both sides, but it doesn't look that way, right? Because k times k minus 1 factorial is k factorial. So that is the trick. Let me say that one more time. I multiply k to the numerator, and that's why we have n factorial k, but I'm also multiplying k to k minus 1 factorial with the denominator. K times k minus 1 factorial is k factorial. Why? Because k minus 1 factorial is k minus 1 times k minus 2 times k minus 3 and so on. K factorial is the same thing, except it has got one extra term of k. Okay, so that is the kind of trick that you can do with factorial that may not be that you may not be used to. Okay, because we normally do not deal with factorial that much in other classes. From line 3 to line 4, what did I do? I basically multiply or divide both the numerator and the denominator by n minus k, the whole thing plus 1. Okay, that's one way to look at it. I divide both the numerator and the denominator by n minus k, the whole thing plus 1. Okay, so with the denominator, I'm just eliminating the largest term out of that factorial. So now it becomes just n minus k factorial. But then the numerator gets a little bit messy because now it has to actually divide n factorial k by n minus k plus 1. So it doesn't seem like we're going anywhere. And then what do I do from 4 to 5? Yep. So when you look at line 5, see how we have n minus 1 plus 1 and n minus k plus 1 both multiply to the numerator and the denominator here? And this entire thing was just n factorial. Okay, so it's just multiplication by 1. Okay, except that 1 is expressed as n minus k plus 1 divided by n minus k plus 1. Okay, and how is that going to get us to anywhere? So we move from line 5 to line 6. Okay, so on line 5, you start to notice that when you look at these two terms, hey, they got the same denominator. Cool. So we can just combine these two fractions into one. And when you look at this part here, they look the same too. So now we can combine these two. So we end up with this expression here. Okay. And then from 6 to 7, what did I do? I just moved things around a little bit, right? So all I did from line 6 to line 7 is I moved this denominator of the numerator to the denominator of the whole thing. And that's it, okay? There's not much else. So I'm still keeping this term here. Are we good so far? And then from 7 to 8. So from 7 to 8, it looks like, oh, we magically make it simpler. Well, there are two things that I did. One is I look at n minus k factorial times n minus k plus 1 and go like, isn't that really just n minus k plus 1 factorial? Because we're just adding one more term to an existing factorial and extend it to the factorial of the number that is one larger than what it used to be. Okay, so that's what I did with the denominator. What about the numerator? Canceling. Okay, because we got subtraction of n factorial k, and then we got n factorial k as a term that we add. So those two just cross out, they cancel out. So now we got this, and then from here to here is really just the algebra. So instead of expressing n minus k plus 1, we express it as n plus 1, the whole thing, minus k. And that's just done by associative rules of algebra. Okay? And when you look at this, then you go like, hey, that fits into the format of n plus 1 choose k. So that's the whole proof. It's a direct proof just using algebra. The only tricky parts of this is how we do something like this. splitting, factorial and merging in factorials. So those are the things that you normally do not do with, like usual algebra, because we don't normally do a whole lot of factorial stuff. So are there any questions about this proof? What is it for? Right? I mean, that's one thing that I really encourage everyone to think about when we talk about certain topics. It's like, why were we talking about this? How does this relate to everything else that we have already talked about? That's really important, because that's how your brain can remember concepts and understand concepts. Because understanding is relating a concept with other concepts using logic. Okay, all right, so now we know this, and do you know this rule, okay, this Pascal Identity? Have you learned this Pascal Identity from high school in the form of the Pascal triangle? Very good. Huh? Summation? Okay. But you can also look at it as a triangle. The Pascal's triangle is the result of Pascal's identity. Does everybody understand that part? Why the triangle is really just one way to visualize this particular theorem. Are we good? Okay, all right. So now we look at this and go like, now we can look into what we call the binomial theorem. This is the binomial theorem. Okay, so we'll go ahead and take a look at the binomial theorem by itself. Okay, so this is the binomial theorem. So the binomial theorem, even though I use the for all, the quantifier stuff and whatnot, all it really is saying is, okay, so if you don't really like the quantifier stuff, just, not ignore that part, okay? So all it really is saying is p plus q, the whole thing to the power of n, can be expressed as a summation of the index I going from 0 to n, and in each term that we are summing over this sigma is n choose I, and then some power of p, which is to the power of I, some power of q, which is n minus 1. This is a typo, the backtick, just ignore that backtick. But other than that, other than the confusing backtick, do we have any questions about this theorem? No? Okay. Does this theorem answer a question that we had earlier? What is Ki? Yeah, exactly. This is Ki. So now we know the quantity of each product of p to the power of I, q to the power of n minus I. Okay, now we'll go back and explain the importance of knowing this combination, okay? But for now, our focus is, well, Tech, you can claim anything you want, right? I would like to see the proof of this theorem. I know most of you do not, but I'm just going to assume that you want to. Proof by induction, okay? Now, proof by induction is really, really cool. We talked about it a little bit, I think. Did we? We did not? Okay. So we'll prove it by induction, which is, I think this might be actually the first time we get into proof by induction. So I'll explain that a little bit. So in proof by induction, the first step is to establish what we call a base case. Base case, all it means is to say, let's not consider every n that is possible here, because there are an infinite number of value of lowercase n where this theorem is supposed to apply, right? So we'll just fixate on 1 and say, can we prove this theorem when n equals to a particular value? Okay? And typically, not always, but typically it is convenient to pick n equals to one end of the range of the values when there's a natural, extreme end. So in this case, because n is supposed to be coming from the set of natural numbers, we do have one, natural minimum n that we can just say, hey, we can pick that guy, okay? So we choose n to be 0 in this case. So now the question is, can we prove this theorem but only when n equals to 0. That very specific case. Okay? So now we say, well, let's try it. So we are now looking at p plus q to the power of n, but n equals to 0. So we are now looking at p plus q to the power of 0. And we all know anything to the power of 0 is 1. Okay, cool. But the theorem is not proven yet. Okay? Because what you need to do is to say, can we express that as that thing? So now in this case, because n is 0, so I goes from 0 to 0, and we are looking at 0 choose 0 times p to the power of 0 times q to the power of 0. Does that work? Okay? So let's look at those terms one by one. 0 choose 0. What is 0 choose 0? 1. How do we know that? Because by the definition of combination, you know that. What is the definition of combination? In this case, it is n factorial divided by I factorial times n minus I factorial. N is 0, and 0 factorial is the numerator. I'll get to you. I is 0, and then n minus I is also a 0, right? So we are looking at 0 factorial over 0 factorial times 0 factorial. 0 factorial is 1 by definition. So we got 1 divided by 1 times 1, which is 1. That is this one here. P to the power of I is p to the power of 0. That's 1. N is 0. I is 0. N minus I is also 0. Q to the power of 0 is 1. So we are looking at 1 times 1 times 1, which is 1. Oh, great. Yep.
Why are we even bothering with that for summing from 0 to 0?
We are summing from 0 to 0. That means we have one term.
Okay.
Yep. So this is the whole thing. Okay. We basically, instead of just stopping here, okay, I change it all the way back to the form where it is now becoming, part of the theorem. Is that okay? So when I ask you to prove something by induction, you have to make sure that you do the same thing as well. Okay, you have to basically prove that the base case is when the theorem is true for a specific case. But you have to basically show me that this is the form of the theorem, but only when n equals to 0. Are we good so far with the base case? So it doesn't sound too hard, right? With most theorems that can be proven by induction, the base case typically is pretty simple. Okay, it's just algebra, move things around a little bit, and you're done. So you want to pick the extreme. So if you're dealing with natural numbers, 0 is a natural number to choose because it is the smallest one. Sometimes you can't really choose an extreme, like if I have a theorem that applies to all integers, then you have a problem, right? Because integers go negative and go positive. There's no one single number that is quote unquote the end on either side. So in that case, you would have to choose 0 most of the time. But then you have two induction steps, one to go to the positive side and one to the negative side. So we'll explain that when we get to that point. Okay. All right, so now we get to the induction step. The induction step is trickier, okay? So you really have to understand the point of the induction step. So in the induction step, it is a two-stage step by itself. The first stage is we make an assumption, okay? So we make the assumption that the theorem is true for some arbitrary k equals to n equals to k, okay? So you have to be careful because the assumption is not that the theorem holds true for all k for n, because that becomes circular reasoning. Are you guys catching that? Okay, so the assumption, okay, I'll say that one more time. So the assumption in proof by induction, in the induction step, is that the theorem is true for some arbitrary n equals to k, a specific k, not all values of n. Okay, because if you make the assumption that it works for all values of n, then it becomes circular reasoning. You cannot assume something that you're supposed to prove. So the assumption is very specific. I'm just going to double check to make sure the recorder is on. Yep, it's on, and I think the mic is on too. Yep. Okay, so we're good. So using this assumption, what we need to do is to prove the following. We have to prove the theorem is also true for the case when n equals to k plus 1. So by making an assumption that the theorem is true only for n equals to k, we try to use that assumption to prove that the theorem is also true for n equals to k plus 1. Are we doing okay so far with that idea? So I can give you a picture to kind of give you a visual of how proof by induction works. Okay? I'm stranded on an island. Okay? And there's a cruise ship over there. And I want to know, can I get to that cruise ship? Okay? That's kind of the question. So part of the assumption that I can also add to this is there are sea turtles along the way between me, on the stranded island, and the cruise ship. And then the next fact is every turtle is within 1 step distance. Okay? So how do you prove that I can actually get to the cruise ship? Proof by induction. Base case is, am I sinking right now? Am I drowning? No, base case is I'm standing on an island. Step 0, right? That's step 0. I'm standing on an island. I'm not drowning. Good. Now the assumption, now we try to prove by induction. So the induction is assuming that I'm not drowning at this point. Okay? Can I make 1 step and not drown? And the answer is yes. Okay? Because there's another sea turtle within 1 step's distance from me. And by combining those two, I have now proven by induction that I can get to the cruise ship without drowning. Is that okay? No, it cannot, because it is some arbitrary k. So the thing about because it's a if, right? Because the assumption is, so the induction step is saying if the theorem holds true for some arbitrary n equals k, then the theorem also holds true for n equals to k plus 1. But I cannot establish whether the condition of the if itself can be true or not. In other words, in this analogy, I'll get to that. So in this analogy, it's kind of saying that if I'm not drowning yet, I can make the next step. But the question is, am I actually drowning at the very beginning of the entire thing? And the induction step cannot establish that. So you need a base case to basically say, yes, where I'm standing right now, to begin with, I'm not drowning. Then you can use the induction step to reason out and say that, oh, so I can take a step and not drown. I can take another step and not drown. So eventually I can get to the cruise ship. Yes? Correct. Yep. So proof by induction is a very powerful proof technique, especially in programming and algorithm proving. And why is that? What reminds you of induction in programming? Loops and recursion. That is correct. Both of those. Okay? Because with loops, it's kind of like I know I'm in a particular iteration, and I know properties of all the variables, how they relate. If I perform another iteration, would these relationship between the variables hold? Okay, that is the loop thing. Recursion, kind of the same thing, right? How deep are you doing the recursion? The base case of proof by induction is corresponding to the recursive algorithm stopping. It's like, oh, we got to the last one, okay? There's no recursion anymore because I know the answer to this one. That is your base case. So proof by induction is a very powerful proof technique because it applies to programming stuff that we do. It can help you prove the correctness or help you validate the correctness of your algorithms. So are we good so far? Yeah, just looking at the context of proof by induction. Okay, all right. So getting back to this specific proof by induction, okay? So in this case, the induction step, basically says we can assume that this is true for some arbitrary k, okay? And k is not even known. I'm not saying that k equals to 0 or k equals to 200. I'm just saying that if the theorem is true for some arbitrary k, I'm assuming that the theorem is holding true already for that one specific value of k. Okay. So now I want to know, well, what can we say about p plus q, the whole thing to the power of k plus 1? First thing we do is we break it apart. Okay. So we break it apart into p plus q, one thing, and then p plus q to the power of k as the second thing. Because p plus q to the power of k was what the assumption was about. So now we can make use of the assumption, because the assumption says, if this is true, then what happens, right? So we are making use of the assumed fact. So using that assumed fact, we expand p plus q, the whole thing, to the power of k, using the assumption. So we end up with this. Do we have any questions about this derivation? Okay, no questions. So now, what do I do to go from line 2 to line 3? Pretty simple stuff. Yep, exactly. So I just move the p plus q, which was outside of the summation, into the terms inside the summation. I can do that because p and q has nothing to do with I, which is the indexing variable. So I can actually move it in or out if I want to. Okay. And then what do we do? Let's see. Okay. So between line 3 and line 4, I just separate one side to deal with p and the other side to deal with q. Because if you look at this, if you expand it, it really is just saying that every p to the power of I is now becoming a p to the power of I plus 1, because that's an extra p now. Okay. And if I distribute q to the other side, then it's kind of the same thing, except this time q has one extra power in these terms. So are we good so far? So I'm just moving things around a little bit. And then we get to this one. Okay, this is a little bit wider than what the screen can do right there. Okay. So what I'm doing here is a little bit of a cheat here. Okay. So can someone tell me what did I do from here to here? Yep. Exactly. So I look at this summation here and I go like, well, I'm going to take the first term out of the sigma to have its own entry here. And then I just change the indexing so that it goes from 0 to k minus 1. But it's okay because I am adjusting some other things to make up for that. Actually, let me take a look here. No, I take it back. This term, the last term of this is separated out to go over here. Okay, so I misspoke. If you take what is the last term of this sigma? Is when I equals to k, right? So when I equals to k of this term, then we have p to the power of k plus 1 times q to the power of k minus k, which is 0, right? And then the choose here is going to be k choose k. I take that term and I separate it all the way out here. Then you go like, no, you did not, okay? Because we have k choose k here, and you have k plus 1 choose k plus 1 here. They're the same, because anything choose itself is 1.
So why would you put plus 1 down?
Well, it'll be revealed later, okay? No spoilers. And then I do the same thing here, okay? So this one is corresponding to this one, except I took the first term out, so that I go from 1 to k now. So if you look at the first term of the second sigma, it is k choose 0, right? Times p to the power of 0 times q to the power of k minus 0 plus 1. That's kind of like this guy here, right? Then you go like, but wait, k to choose 0 is here, but we have k plus 1 choose 0 here. How does that work? Because that's also 1. Okay? Anything choose itself is 1. Anything choose 0 is also 1. Now, if you expand the equation or the formula of k plus 1 choose 0, you can see how it is 1. But intuitively, it makes sense too. I give you a box, okay? I don't even know how many things are in the box. And I'm asking you, how many ways can you choose nothing out of the box? Okay? Now, what about this guy here? I give you a box. I have no idea how many items are in the box. And I'm asking you, how many ways can you choose everything in the box when ordering is not important? 1, because I just choose everything, right? So that is why, anything choose itself, choose that same number, is 1, but anything choose 0 is also automatically a 1. But I abuse that fact and just change the k into k plus 1 here, and then change the k to k plus 1 over here. So now, with this, what am I doing here? From this row to this row. These two terms are now kind of like, they're looking closer, okay? And I can just manipulate things a little bit so they can look even closer. So the only thing I did was with this term here, it became this. All I did was to change the indexing. It used to go from 0 to k minus 1. Now it goes from 1 to k. Then you guys go like, but you cannot do that because the index is actually used in the equation in each term to do some calculations. Fine. Since I am now 1 more than before, the index itself is consistently 1 more than before, everywhere I see the index is now the index minus 1. I just offset everything back so that we get the same term except the index is expressed differently. Is that okay? So it's only from here to here that makes the difference between those two rows. But when you look at this line here, then you go like, oh, since both sigmas are going from 1 to k, we can combine that back into one single sigma because they have the same index range. Is that okay? So now we have one single index range here, where each term inside the index range has the same power of p and the same power of q. Because when you look at this and you look at this, hey, they're exactly the same. The only thing that is different is how many of those things. We got k choose I minus 1 here, and then we got k choose I over here. So that's why we factor those out, and it becomes k choose I minus 1 plus k choose I. And that becomes the quantity of the product of power of p and the power of q. Now, what does that remind you of? Pascal's identity. That is why we studied Pascal's identity, is so that we can do this. So all we did here is to take this sum of two combinations and put it into here. That is due to Pascal's identity. Is that okay? So now things are looking pretty cool because where we had k plus 1 and then we have k here and things are all over the place, now we consistently have k plus 1 choose 0, k plus 1 choose 1 through k, and then k plus 1 choose k plus 1. Oh, we can now fit the entire thing into one gigantic sigma, right? Because we can extend this I equal to 0, I equals to 1 to I equal to 0 to cover this case. But instead of ending at k, I can now make it end at k plus 1 to also handle this case. So after that simplification, we got this form. But that's exactly what the theorem wants. So QED, we're done. So are we okay so far with the binomial theorem? This is called the binomial theorem. The proof of the binomial theorem is okay. All right, cool. And if you look up on the internet of proofs of the binomial theorem, you might find something different, because this is really just my version of the proof, and there might be shorter and more elegant ways of proving the binomial theorem. So it doesn't hurt, okay, to read other proofs, just to get an idea of how other people prove it, okay. But I cannot teach anything that I cannot do myself. So that's why I have to put all the proofs into the modules. Okay. Okay, so the trick and stuff like that. Okay, so now we get back to the question: why do we care about the binomial theorem now that we have proven it, right? Okay, so I'll just give you a case. Okay, I'll give you an example. Let's just say that a coin is loaded. We know that the chances of landing on the head is 70% of the chance, okay, which is pretty extreme. And then the chances of landing on the tail is 0.3, okay? So now I'm asking you, and I say, would you bet on 2 head out of 5 tosses? Exactly 2. Okay? Or I can ask you, what is the probability that it will have 2 tails out of 5 tosses? Or if you prefer, we can also change the question to at least 2, or at least at the most 2. Okay, so the number is kind of like maybe not, because the probability of each toss landing on the head is pretty good. Okay, but we only want to look at 0, 1, and 2. Is that enough to improve my chances to be more than 1/2? Basically, that's the question. Okay, so let's go ahead and analyze that question. And I'm going to use a notepad to explain that portion. Okay, so we'll say the probability of a head is known to be 0.7. The probability of a tail is known to be 0.3. Okay, so we'll call this P, and we'll call this Q. Okay, just to use the same symbol or variable names that we have been using already. So now the question is, what are the chances that out of 5 tosses we end up with at least 2, well, at the most, okay, at most 2 heads. Okay, so if someone says, okay, do you want to place a bet? Okay, if we end up with at the most 2 heads, you win. But what are the chances it will end up with at least 2 heads? At the most 2 heads, actually, at the most 2. Versus, 3 or more, right? Okay. So let's work this out. So we know that P plus Q to the power of 5, okay? Now remember, do not use the caret symbol in C and C++ to mean to the power of, because in C and C++ it means exclusive OR, which is not very different from to the power of. But in text, this is how I like to put it, because it's, I don't need to use the power function. Okay, so it has got a whole bunch of P to the power of 5s, right? How many of those do we have? 5 choose 0 of those. Okay, so we have 5 choose 0. I'm flipping the vertical thing to horizontal. Is that okay with you guys? Okay. And it has 5 choose 1 of P to the power of 4 times Q, right? It has 5 choose 2 of p to the power of 3 q to the power of 2 plus 5 choose 3 times p to the power of 2 q to the power of 3 plus 5 choose 4 of p to the power of 1 q to the power of 4, and then we have 5 choose 5 times p to the power of 0 q to the power of 5. Okay, and we know this they all have to add up to 1. Okay, that part is known. So out of this entire equation, which part are we interested in? When we want to find out what are the chances of out of 5 tosses, we end up with at the most 2 heads. This one is corresponding to 5 heads, right? Not interested. 4 heads, not interested. 3, not interested. Yep, this one we want, okay? So we'll just indicate that this is what we want. This one has 1 head. Yep, we want that. And this one has no head. Yep, we want that too. So now it's just a matter of putting this into a calculator, find out the exact value of those things, add them up. If it is more than 1/2 of a chance, yep, it's worth it. Place your bet. Yep.
You're just looking at the exponents on the p to decide it, like which one's correspond how many heads?
Yep. Now you can also you can always flip the indexes, right? You can say this is 5 choose 5, 5 choose 4, 5 choose 3, 5 choose 2, and so on, because they're all symmetric. So so you can choose which one, how to increment the number of things that you choose from. Because by choosing the number of heads, you have just chosen the number of tails. Yep.
So like you expand out your binomial, and then you take whichever ones correspond to the thing you want, add those up, and that gives you your probability for the one thing you're asking about.
For the event that we're interested in.
Okay, and if it were exactly 2 heads, then you would only pick the one with p to the 2.
Yep. Okay. Exactly. Yep. So let me just repeat that because I want the mic to capture that too. So this one here is only for the case when we have exactly 2 heads and 3 tails. This one is only for 1 head and 4 tails, and this one is for no head and 5 tails. But since what I'm interested in is at most 2 heads, so that would have to include 2, 1, and 0 heads. And that's why we have to sum up all the underlined items. Okay? So I'm curious, okay, if I were to, gamble, okay, what are the chances? So, huh?
You take bets now.
That's kind of what the lotto fund is for, okay? When people buy lottery, the money that is made by the state government, a good portion of that is actually, sent to community colleges and other K-12 institutions. So we actually have a fund called Lotto Fund. I'm not kidding. It's actually called the Lotto Fund, and we can use that fund to buy anything less than $200 that we can use consumables basically in classrooms. So we just got some allocation for the design hub for next semester. So we'll be buying a bunch of Raspberry Pis, Arduinos, and I'm proposing that we buy some Chromebooks too, because Chromebooks can now run because Chromebooks can run Chrome. Okay, that's kind of given. But you can use Chrome to run a web version of Arduino, and you can also use Chrome to run a web version of SSH client. So using a Chromebook, you can now program an Arduino or a Raspberry Pi remotely. So that means a Chromebook is actually not a bad development tool, given that now we have all of these super duper web-based tools. And then of course there's also Replit, repl.it. So it's a platform online, web-based, and you can experiment and program in just about any programming language, except for Ransom. That's a programming language that Kevin kind of invented. Okay, so for anyone who's interested, you can actually go ask him. Kevin Kirby, he works at the Design Hub and also the Mesa Center. But basically, Ransom is called Ransom because he is using like fonts, boldface, underline, italic, to mean different things. So when you write your program, it looks like a ransom letter. Yep. So that's okay. I mean, that's kind of cool. Okay. So we are looking at combin, COMBIN, 5, choose this number. And okay, I forgot to put in the probabilities. So we got 0.7, and then we got 1 minus 0.7. Okay, so we need to look at this and say multiply that by this one to the power of 2 times power, the second one, and then 5 minus this number. Okay, and then we have to make sure that they do not float with the row numbers. So all the row numbers, some of the row numbers cannot change. So that can change. This one cannot change. This one also cannot change. I think that should be it. Okay, so let's check it out. Okay, and then we add up these three numbers. So you only got that looks awfully low. You only got a 16% chance of ending up with, at the most, 2 heads out of 5 tosses. Even though the head is, huh?
What number is that? What number did you get?
0.16308. Yep, so that's pretty low. So we'll try to load the coin more. Oh, okay. I can change the font here, or zoom factor, so we can. There you go. Is it better?
Yeah.
Okay. Yep. So let's load it even more. Let's load it to 0.75, 95% of the chance. It goes the opposite way.
Yeah, because you're betting on a low number of hits.
Yep. So if you go the opposite way, then we should have a higher probability, right? Let's say 25% of the chance. Now it's good. So is that okay? Now, there are many ways I can ask questions related to this. Okay, you can study some of the past exams to know how I ask questions. But, over these years, if someone has the patience to collect all the past exams, I mean, there are only so many ways for me to ask questions about a particular topic. Eventually, I will run out of ideas. So I'm not sure whether this is the year where I run out of ideas or not. Okay, but in one of the exams, I had an auditor go into a casino to observe, coin tosses to see if the coin is loaded or not. Okay, sounds like a reasonable thing for people to do, right? So here's the observer, picking up some cocktail drinks here, some other drinks over there, and counting, okay, out of 5 tosses, this has, this many heads. Out of 5 tosses, this has this many heads, and so on. So at the end of the day, because of the alcoholic beverages, this auditor lost some of the data. And what is only left is, okay, I can only keep track, I only have the total number of, out of 5 tosses, 3 heads is this number, okay? And I can still remember, or there's another way to track the total number of, experiments performed. The question is, out of only these 2 pieces of information, can you go back and deduce, whether the coin is loaded or not? It's kind of, well, if you want to look at the likelihood, that is the case. But at least you can tell whether it is close to not loaded or not, right? So out of the observation, based on the observation, what is, the probability of landing on the head and the probability of landing on the tail? It's not going to be 0.5, okay? It's going to be some number, but it's not going to be 0.5. The question is Is it like 0.502, which is like, okay, it's we know that it's not going to be exactly 0.5. So 502 is close enough. Or is it like 0.7? I mean, this is like, no, this cannot be, right? So what do you think? Can we do something like that? Yep. So the answer is yes, you can definitely do it. So what you do is we have to extend this a little bit. And, okay, insert row. And then we have a 3 here. And then drag this up. Okay. Does that make sense? Yep, still makes sense. Okay, so if I change this back, yep, okay, so everything is still making sense. So if the coin were even, okay, it's not loaded, then we would have a 31% of the experiments ending up with 3 heads out of 5 tosses. Is that okay? So if the observation says, out of the observations of 5 tosses, and this percentage, observed percentage, is 0.16, we know something is not right. Okay. Alternatively, when we look at this when we look at the actual observed number, and this is like 0.56, we also know that something is not right. Because the observed percentage of the chances of the times when out of 5 tosses you have 3 heads should be close to 31.25%. It won't be exactly the same just because it's chances, but because there's so many experiments performed, the certainty that it should be 31.25% is becoming higher and higher. Okay, it cannot distribute further as you have more experiments. That is called, there's one term to describe that phenomena, and I cannot remember what it was. It's actually supposed to be one of the things that I need to teach in this class, but I cannot remember the term of that. So let me just go back to the syllabus of this class because it is in the syllabus. Huh? No, standard deviation is a statistic thing, and this is not. So we want to look at the section dependent information. It is one of the learning outcomes. So, nope, it's not here. Law of large numbers, that's it. So the law of large numbers is just basically, it's not based on actual math. It is just, an argument to say that, if you have a lot of observations, then it should reflect the quote-unquote truth better. So if you only have 10 observations of these experiments, and it is 35%, okay, instead of 31.25%, then go like, yeah, well, only with 10 experiments, we expect that number to be able to fluctuate quite a bit. But when you have performed 1,000 observations and the average is still 35%, then you go like, something is not right. This coin is loaded, or very likely to be loaded. There's a very slim chance that it is not loaded and still give you that number, but that chance is becoming very, very slim. As opposed to one observation, okay? You only observe one experiment, and it goes like, well, then in that case, it's either 1 or 0. It's either 100%, it is 3 heads out of 5 tosses, or 0, it is not 3 heads out of 5 tails. Can you make a conclusion that the casino is cheating when you only make one observation? No. Because you'll be accusing the casino either way in this case. Because none of that number, 100% versus 0%, is close to 31.25%. Okay? So that's the argument, based on the law of large numbers. Cool. So the binomial distribution is what we just talked about, and this is singling out a particular term. So are we okay so far with all of this stuff? Okay. And do you guys still remember how this might still relate to computer science? Particularly transmissions, things that can be probabilistic. Okay, so when you transmit a bit, like a 1, do you know whether it's going to be received as a 0? Well, you can collect statistics, right? Because it has to do with the temperature of the semiconductor, it has to do with the transmission medium, it has to do with a whole lot of factors. But you can design experiments and find out, what is the error rate of your transmission. So if you transmit 1, like 1,000 times, okay, it might be received as a 1 995 times. But the other 5 times is erroneous. It is received as a 0. Is that okay? And if you assume a 0 also has the same error distribution, which sometimes is not true, but let's make that assumption, then it is a question of, it's a coin toss again, where landing on the head is kind of like, yep, I received what I'm supposed to, and landing on the tail is, nope, I did not receive what I was supposed to. So now the question is, if you have a packet, okay, at a hardware link level, you have a packet of, let's say, 2048 bits, okay, what are the chances that that packet will be received correctly entirely? That might be something that you're interested in, right? Because if you know that probability that a packet of, a certain, width is going to be received correctly, the entire thing, then you can say, oh, okay, now we can actually compute the effectiveness of this communication method. Because otherwise, if it's received incorrectly, assuming that it can be detected that it was not received correctly using CRC checksum or some other way, then it has to be retransmitted. So that would basically decrease the effectiveness of whatever transmission mechanism that you're studying. So it is still binomial distribution because it's either received correctly or not received correctly. Okay, and you can get the probabilities just by performing experiments, under controlled environments. Like, hey, go turn on that, microwave oven, and let's run the experiment again. Questions? So that's the actual application of, something like this. Yep, go ahead.
So really, we can figure out by how much something is more likely than the other using, like.
Yes. Or you can go both ways. Okay, if you're given the P and the Q, then you can calculate the probability. Then you can choose whether to do something or not based on that information. You can also be given observations. Then you can go back in time. Well, not go back in time, but you can go back and figure out what is the P and the Q. So it can go in both directions. And it can be helpful in both directions because one can help you decide whether to do something or not, and the other one can reveal the truth based on the observation. So both directions can be helpful. And that's only just using binomial distribution. Now the other stuff, like combination and permutation, that's also the same thing because when should what are the chances that you will win a particular prize in lotto? So let's just say that we are all realistic and say that winning the jackpot is out of the question. Okay, we know it's really hard to win the jackpot. I just want to get some price. Okay, so on the average, am I getting even with how much I spend on lotto? Now, just from the reasoning that I'm getting money, lotto fund, it tells you that it's not going to be even, right? But how uneven is that? Okay, for every dollar that I spend, okay, how many cents am I getting back on the average? So now that becomes another question, right? But this one relates to combination because now you're looking at what are my chances of winning the lowest price of lotto game? What are my chances of winning the next one, the next one, the next one, and the next one? And then you add them up and go like, oh, for every dollar that I spend on a lotto ticket, I might be getting 30 cents back. So, so your loss chances. Then you can decide whether, you feel like, do I want to, lose 70 cents every time you buy a lotto ticket? It becomes an informed decision as opposed to, I have no idea. I just kind of feel lucky today. Then it becomes a more informed decision. It's like, well, I know ahead of time that statistics is against me. I'm gonna lose 70 cents out of a dollar, on the average. But you know what? I can spare that 70 cents today. Okay, and I choose to gamble today. But that's the different decision-making process. Because knowing then choosing how to do things is different from not knowing and go like, yeah, let's do it. So do we have any questions about discrete probabilities? Because this is pretty much the end of the entire slide, the entire module as well. Because let me just kind of go back to this module, and I can show you where we are. I'm not going to give you the next assignment just yet, so I'll wait until Monday to give you that. But I can tell you what it's about so you can actually prepare for that a little bit. And then on Monday, I'll give you that. It's not omega generator anymore. This is now U generator. So I want you to write a program where I can give you the number of trials and then the number of choices of the first trial, and then you have to crank out all the combinations that can come out of it. And we are only interested in combinations, not permutations. That's why if you choose 2 out of 3, we code each possibility as A all the way to Z. So if you choose 2 out of 3, then A, B, AC, and BC are the only combinations. Obviously, when you list it doesn't have to be listed this way. BA is just as good as AB because order is not important. So that's basically your homework assignment. But I'm not assigning it just yet, so you can think about it, but don't do any coding because you don't know the other constraints of this homework assignment yet, okay? But you can think about it. You can definitely start to think about set representation or other ways to keep track of combinations. Because in the past, I usually ask, a generator to generate permutations, but this semester I kind of go like, let's go ahead and just generate combinations instead of permutations. All right. Well, I'm going to end the class 2 minutes early today. So you guys have a nice afternoon and a nice weekend because I'll see you on Monday. Thank you.